Consider you're going to put a certain amount of money into a bond or a savings account or a stock or something like that. You put in P dollars, and after a year they will add to your original amount times some rate. So for example, let's say you put $100 into a savings account, and after 1 year they will give you 10%, 0.1, 10% more than what you originally had. So you'll have the original $100 you put in, plus you'll earn $10 more, and so you'll have $110. So you earn 10% at the end of the year. So the amount of money that you have at the end of the time period will be equal to P plus P times R. And the P's in this equation factor out, and we get 1 plus R. And so if you redistribute the P into the parentheses, you would get P plus P times R. Now let's say that at the end of the second year you will have your original amount, so in this example $110. You'll have the original $110 that you started that second year with, plus they will give you a certain percentage of your money again. So in this example, the second year started out with $110. That was P times 1 plus R, $110. Plus you'll have your $110 again times the 10% interest that they give you. And so at the end of the second year you'll have your $110, the original amount you started the second year with, plus another $11. And so at the end of the second year you'll have $121. So in the first year you only earned $10 because you only had $100 to start. The second year you earned $11 because now you had $110 to start. And so at the end of the second year you'll have 121. So this formula would tell us the amount of money that you would have in your bond or savings account from your initial investment, $100, and whatever interest rate you're earning on that money. And so this is what you would have at the end of 2 years. This is what you have at the beginning of the first year. This is after 2 years. Now if we look at the second year, P times 1 plus R, P times 1 plus R, this factors out, and we get P times 1 plus R times 1 plus R. And so again, if I were to redistribute all of this into this set of parentheses, we would have P times 1 plus R plus P times 1 plus R times R, which is what we started with. And so 1 plus R times 1 plus R is 1 plus R squared. So at the end of the second year, whatever your initial investment was, $100, times 1 plus your interest rate squared is how much money you will have at the end of the second year. And the same type of thing will happen if we look at the third year. You'll have your original amount at the beginning of the third year. You have P times 1 plus R plus, squared. Right, that's the amount you start with the third year with. Plus, at the end of the third year, they will give you P times 1 plus R squared, your original amount you started the year with, times R, right, the new interest rate. So they're giving you interest on your money, plus you have the money you started with. And so again, this factors out, P times 1 plus R squared, and P times 1 plus R squared, that factors out. And we get P times 1 plus R squared, times, we'll be left with 1 plus R. And so what we get now is 1 plus R squared times 1 plus R is 1 plus R to the third. And so at the end of the nth year, however many years we want to leave our money in the bond or the stock or the savings account, we will have P times 1 plus R to the nth power, where n is the number of years that has passed. And so this is the formula that we've been using for interest that compounds each year. the book writes this as y equals a, where they use a for the original amount instead of p, times 1 plus r to the nth power, where r is your interest rate and n is the number of years you've kept your money in that stock or bond or savings account. So we have our formula for interest being compounded once a year. Now let's say that instead of giving you your interest payment at the end of the year, let's say they give it to you halfway through the year, and they give you half of the interest after 6 months, and they give you half of the interest again at the end of the year. And so, for example, you have your original amount you invested, and instead of giving you your full interest rate, they give you half of that rate, that's R, and they give that to you twice a year. And so let's look at the example again of $100. You start out with $100 in your bank account. After 6 months, instead of giving you 10% interest, they will give you 5% interest, 0.05, and that's how much money you will have at the 6-month mark. And so you'll have your original $100 you invested, plus you'll have $5 more. And so you'll have $105 altogether after 6 months. Now, at the end of the second 6 months, at the end of the first full year, you started off with $105, and they're going to give you 5% interest on that $105. And so the interest rate for 5% on $105, 105 times 0.05, means that you get another $5.25. So you have $105 plus $5.25. And so at the end of the first year, you will have $110.25. And so if your interest is being compounded every 6 months rather than instead of every year, you earn slightly more money, right? If it was compounded at the end of the year, you would only have $110. If it is compounded every 6 months, you'll have slightly more, $110.25. And so the rate that we are being paid out is half of the actual rate for the whole year, right, 5%. And we give you your interest money twice a year. And so if I plug my values into this formula, we started off with $100 originally. Our rate was 10%, but they give us half of that rate every 6 months. And instead of giving it to us at 1 year, they'll give it to us twice in the year. And so the formula becomes y equals 100 times 1 plus 0.1 divided by 2 is 0.05. That's our effective interest rate that we get every 6 months, the 5% squared. And so y equals 100 times 1.05 squared. And so y equals 100 times 1.05 squared, 1.05 squared, which is 1.1025. 1.1025. And 100 times 1.1025 multiplied by 100, move the decimal point 2 places to the right, will be $110.25. So this formula gave us the same value as working it out individually once every 6 months. So this formula took care of the interest rate being cut in half and getting our money twice a year instead of just once a year. So we've seen that the interest earned, if your interest is compounded once per year, is y equals a times 1 plus r to the nth power. And the amount that you will have in your account if the interest is earned twice a year is a times 1 plus r over 2 to the 2n power. And likewise, if your interest is compounded 4 times per year, we will have a times 1 plus r over 4 to the 4n power. And so this would be for interest compounded quarterly. Now what if they compounded your interest once every month? It would be a times 1 plus r over 12 to the 12n power. And what if they compounded your interest continuously, infinitely? If they divided your interest rate by infinity and they gave you that interest rate an infinite amount of times, what would happen? And so we can't calculate this with infinity because infinity is a number that is too large for us to calculate with. But we can think about a number that is very large, such as a billion, something like that. And so the formula says that the interest rate that you're earning each time they pay out your interest is extremely small, because your interest rate is being divided by a very large number. But they're giving that interest rate to you an equally large number of times. And so let's see what happens. How much money would you have after your initial investment? And let's say that, just for simplicity, that your interest rate was 100%. Right, so I'm going to use 1 as the numerator. And we're going to divide by a really large number, like a billion. But they give you this interest a billion times in 1 year. Well, let's see. I wrote a trillion down here, so I'll use a trillion. Okay, so how much money will we have? Well, this part of the equation all works out, right? There's no unknowns in this equation. We're saying the interest rate that we're earning is 100%, which is very high, but we're just doing that for simplicity. And they're going to give you that interest rate 1 trillion times per year, and they're only going to give you 1/trillionth of your interest rate each time they give it to you. And so let's see what this all works out to be. So we will have, open parentheses, 1 plus 1 divided by 1 trillion, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, raised to the 1/trillionth power. So raised to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 power. And the number that we get, this all works out to be 2.71828. 718281828, and this will go on forever. My calculator can only show 8 digits, but it goes on forever. This number, 2.718, that is Euler's number. E to the first power is 2.718281828. And so this all works out to be Euler's number, and that's where the base of the natural logarithm comes from. When we talk about natural log, we mean the log where the base is e, and we mean e as being 2.718281828, and this goes on forever without repeating. That is the natural number, and that's where this number comes from. This is example 1. It says, how long will it take $5,000 compounded quarterly at 6.4% to accrue to $8,000? So we're going to invest $5,000, and we're going to earn 6.4% interest, and we want to know how long does it take, in other words the time, how much time does it take for our investment to accrue to $8,000. So $8,000 is the amount that we want after some amount of time. $5,000 is the original investment. The interest rate is 0.064. Our interest is compounded quarterly, so we're using 4 in the formula. And we want to solve for n. That is how many years. N is the number of years that passes. So how many years does it take? And so to solve for n, our goal is to get n by itself. We could use logarithms to get the exponent out as a multiplier, but before I do that I need to get rid of the 5,000. So I'm going to divide both sides by 5,000. Okay, and this cancels over here. Over here the fraction reduces, all the zeros can cross off, and this becomes 8/5. This will be equal to 1 plus 0.064 divided by 4, all to the 4n power. So to get the n out of the exponent, I need to take the logarithm of both sides, and it doesn't matter which logarithm I take, natural log or common log. I'll use the natural logarithm. Take the natural logarithm of 8/5 on the left hand side, and take the natural logarithm of 1 plus 0.064 over 4 to the 4nth power. And so now I can bring the 4n out because I've taken the natural log of both sides. And so we get the natural logarithm of 8/5 is equal to 4n comes out times 1 plus 0.064 divided by 4. Now I can solve for n by dividing by 4 times 1 plus 0.064 over 4 on both sides. so that the 4 cancels and everything in the parentheses cancels, and we'll be left with n. And so n will equal the natural logarithm. Oh, and I forgot to write my natural log here. Right, I had natural log of everything in the parentheses. I can't forget to write the natural log there. So I have natural log of 8/5 divided by, and again I'm supposed to have natural log here, that's what I divided by, and here, 4 times the natural log of 1 plus 0.064 divided by 4. Okay, and so now we can solve for n by plugging this into the calculator. And so we have in the numerator, the natural log of 8/5, and that is being divided by all of this, so I want to make sure I put all of this in parentheses, open parentheses, 4 times the natural log, and I get open parentheses with natural log automatically, 1 plus 0.064 divided by 4, close parentheses, equals. And in, we get 7.4. And that's going to be the number of years, 7.4 years. So in this formula, the n stands for the number of years that has passed, right? So 4 times a year and 1/4 of the interest rate, that means each year. And so the interest is only compounded quarterly. And so 0.4 of a year, that's not quite 2 quarters. So we get our interest at 7.25 years. We get interest compounded again at 7.5 years. And so 7.4 years is not quite long enough because we don't get interest at that specific time. We don't get our interest again until 7.5 years. And so we want to make sure that we round this up to be 7.5 years. This is example 2. It says Mary and Sid deposit $2,500 into a savings account that pays 3 1/4% compounded continuously. And how many years will the amount in the account double? So we start off with $2,500. We're earning 3 1/4%, or 0.0325. And we want to know how long does it take for the money to double, the amount of time t. And so since they said the interest is compounding continuously, we're going to use the formula y equals a times e to the rt power. So we'll plug in our numbers. Y is the amount that we're looking for after some time, 5,000. A is the initial investment, 2,500. E, which is the natural number, and the exponent is r, which is the interest rate, times t, which is the amount of time, which is what we're looking for. And so we want to start, if we want to solve for t, we want to start by dividing by 2,500 on both sides. I can't take the natural logarithm of both sides until I get rid of any multipliers over here. So 2,500 cancels, the zeros cancel out, and 50 divided by 25 is 2. So we get 2 equals e to the 0.0325 t power. Now I can take the natural logarithm of both sides, and I definitely want to use the natural logarithm because the base is already e. So we'll have the natural logarithm of 2 is equal to the natural logarithm of e to the 0.0325 t power. That allows me to bring the exponent out as a multiplier. So we will get 0.0325 t times the natural logarithm of e. And if you remember, the natural logarithm of e is 1, and so that cancels. Now we can solve for t by dividing both sides by 0.0325. Cancels over here, and we get t equals the natural logarithm of 2 divided by 0.0325. And so we can plug this into our calculator. Take the natural logarithm of 2, close parentheses, divided by 0.0325. And we get 21.328. 21.328. Okay, and t in the formula is measured in years. That is how many years it will take. And so depending on where you round, it's going to take at least 21 years for our money to double in this account. This is example 3. It says the amount of a decaying radioactive element is given by the formula y equals y sub o times e to the negative 0.4 times t power. and it says, how long will it take 50 grams to decay to 25 grams? So they gave us the formula to use already, and this is in the form of the continuously growing or decaying in the form. And so notice that the exponent is negative. That tells us that we're looking at decay rather than growth. They gave us the original amount, y sub o is 50 grams, and y is the final amount, was 25 grams, and they want us to find t. And so we'll plug in our numbers. Y is 25 grams, yo is 50 grams, and times e to the negative 0.4 t power, and they want us to solve for t. And so we'll start by dividing by 50 on both sides. This cancels. And 25 divided by 50 is 1/2, or 0.5. This will be equal to e to the negative 0.4 times t power. Now we can take the natural logarithm of both sides. Natural logarithm of 0.5 is equal to the natural logarithm of e to the negative 0.4 times t power. Now I can bring the exponent out as a multiplier. The natural logarithm of e is 1, and so that cancels. And what we're left with is negative 0.4 t. We want to solve for t, so we're going to divide by negative 0.4 on both sides. That cancels, and we're left with t. And so t will equal the natural logarithm of 0.5 divided by negative 0.4. And so we'll plug this into the calculator. We have natural logarithm of 0.5, close parentheses, divided by negative 0.4. And we get 1.733. 1.733. And so that means it will take 1.733 years for 50 grams of this radioactive material to decay down to 25 grams. This is example 4. It says in section 9.4 we define pH as this formula. pH is equal to the negative logarithm of H+, where H+ is the hydrogen ion concentration. And so it says vinegar has a pH of 2.2, find H+, which again is the hydrogen ion concentration measured in moles per liter. And so they told us the pH was 2.2, so I'm just plugging into this formula, equals negative logarithm of H+, and they want us to solve for H+. First thing I need to do is get rid of the negative. I usually don't like negatives being with my logarithm. I'd rather that be on the other side. And so 2.2 divided by negative 1 is negative 2.2. And this will be equal to a positive log of H+. So again, I want log to be positive if I can. And so log, this is the common log, right? We didn't write a base, so the base is 10. We can rewrite this in exponential form. The base is 10. The exponent is negative 2.2. And the power is H+. So I just rewrote the logarithmic equation into an exponential form. And so now we can plug in our numbers into the calculator and solve for this. We have 10 being raised to the negative 2.2 power. And we get H+ is equal to 0.00631. And so this will be the concentration measured in moles per liter. This is example 5. It says in section 9.4 we define the intensity level of sound as beta equals 10 log I divided by IO. And it says, what is the intensity in watts per centimeter squared of street traffic sound that has an intensity level of 75 decibels? And so I sub O is a constant. This is what we call the threshold of hearing. This is the faintest sound that the human ear can hear. And so that's a constant. They told us that beta is 75 decibels, and they want us to solve for I. So we'll plug these numbers in. We have 75 decibels is equal to 10 times the common log of I divided by IO, where IO is 10 to the negative 16th power. And so we want to start by dividing by 10 on both sides. These will cancel, and we get 7.5 is equal to log base 10 of I over 10 to the negative 16th power. And so we can rewrite this in an exponential form. The base is 10. The exponent is 7.5. and the power is I divided by 10 to the negative 16th power. Now we want to solve for I, so we'll multiply both sides by 10 to the negative 16th. These will cancel, and we'll get I equals 10 to the negative 16th times 10 to the 7.5 power. And so we can plug this into our calculator and solve. 10 to the negative 16th times 10 to the 7.5 power. Oops. See, I typed it in wrong. My calculator, after I am finished typing in an exponent, I have to hit the right arrow to type in things that are not in the exponent anymore. So 10 to the negative 16th power, now I have to hit the right arrow, times 10 to the 7.5 power. And we get 3.162 times 10 to the negative 9th power. So this is the intensity of the street sound, and it's measured in watts per square centimeter. And you can see that the threshold of hearing is times as 10 to the negative 16th power, which is a very small number. This is 3.162 times 10 to the negative 9th. This number is slightly larger, and so the intensity of sound of the street traffic is significantly more intense than the threshold of hearing. This is example 6. The book starts by giving us this formula in a general form. This is a formula for continuous growth that grows towards some bound. And so unlike our continuously compounding interest, with continuously compounding interest we would have gotten a graph that looked like this, where the amount in our bank account continues to grow, and it grows and grows and grows. This formula is slightly different. This deals with values that grow exponentially, but they grow towards some bound. And so this graph will never cross the line A. It will continue to get closer and closer and closer, but never actually get there. And so this is the general form of the equation. Then they give us a more specific form of the equation. It's the same equation, except this deals with capacitors in a DC circuit. And it says that the voltage across a capacitor in a DC circuit is equal to the maximum possible voltage, which is usually the supply, the source in the circuit, times 1 minus e to the negative t divided by RC power, where t is the amount of time that has passed, and R and C are the resistance and the capacitance. So they give us some values for resistance and capacitance, the voltage on the capacitor, the bound, or the maximum possible voltage the capacitor can have, and they want us to solve for t. So we just need to plug these numbers into the formula and then solve for t. So VC is 45 volts. That will be equal to V, which is 75 volts, times 1 minus e to the negative t, which is what we're solving for, divided by R times C. And so R is 3.0 times 10 to the 6th, and C is 6.5 times 10 to the negative 6th. And so we need to start by dividing by 75. So we're trying to solve for t, and it's in the exponent of e. We need to get e all by itself with its exponent before we can take the natural logarithm of both sides. So we start by dividing by 75 on both sides. These cancel, and 45 divided by 75 is 0.6. That'll be equal to 1 minus e to the negative t divided by, and while I'm at it, I'll go ahead and multiply these together. I have 3 times 10 to the 6th times 6.5 times 10 to the negative 6th, and we get 19.5. So this denominator of this fraction, this is all the power of e, the denominator here all works out to be 19.5. Okay. Now I can, I don't really need the parentheses here anymore. Now I can subtract 1 from both sides. These cancel, and we're going to be left with negative 0.4 is equal to negative e to the negative t over 19.5 power. I can divide both sides by negative 1, and that cancels the negative on each side, and so we get 0.4 is equal to e to the negative t over 19.5 power. And so now we can take the natural logarithm of both sides, get the natural logarithm of 0.4 is equal to the natural log of e to the negative t over 19.5 power. That allows me to bring the exponent out as a multiplier. So you get the natural log of 0.4 is equal to negative t over 19.5 times the natural logarithm of e. The natural logarithm of e is 1, so that cancels. And I'm going to want to multiply both sides by negative 19.5. That cancels the negative and the 19.5 over here, leaving us with t. And so t equals negative 19.5 times the natural logarithm of 0.4. So now we can type this into our calculator and get an answer. Negative 19.5 times the natural logarithm of 0.4, and we get 17.87. T is 17.87. In this formula, t represents the time in seconds, and so this will be seconds. It takes 17.87 seconds for the voltage to rise, or I should say fall, actually. Fall from 75 volts to 45 volts. Again, this is a DC circuits type of problem.